Hello, my name is Markus Kettler from Graz University of Technology, and today I will present you a new proposal for the calculation of the local stresses in crane runway girders. This is a crane runway girder made of steel. On the top, a crane rail. The upper flange consists of a U section, and the web plate is significantly higher than shown here. The bottom flange consists of a main plate and an additional lamella. The topic for today are the local stresses in the web plate at this position here, and following the rules in Eurocode 3 part 6 for crane supporting structures, we can calculate the compression stresses in the web, the vertical compression stresses. Based on a wheel load of 100 kilonewton, we get 37 megapascal compression. Usually this wheel load will not always be concentrically, therefore the engineer has to take into account an additional eccentricity, 15 millimeters in this case, and following the rules in Eurocode we get additional torsional deformations of the upper flange and bending in the web. We see again approximately 37 megapascal. For the fatigue check, for the fatigue design, the engineer now has to take the sum of both of those stresses. So 37 times 2 would be the stress to be considered in the calculation. This girder shown here was a real girder, and it was in use for approximately 40 years, so quite a long time in the steel producing industry. And during its lifetime, some cracks occurred. So they had problems with the welds between the upper web and the upper flange. And the engineers had the idea to strengthen the girder, and it was done with additional reinforcement plates, here shown in red. And with these additional plates, the upper flange now shows a box section with significantly higher torsional stiffness. And the idea was, therefore, the torsional stresses will be reduced significantly. And we can see the deformations are reduced and the torsional stresses at the point below the reinforcement plates reduces to 0, just 1 megapascal, and we had 37 at the top of the web. The compression stresses also reduces because we have still 37 megapascal at the top of the web, but it decreases with the web height, so we here just have approximately 19 megapascal. So we have a situation below the reinforcement plates which is perfectly fine. Within the box section, as mentioned, the compression stresses from concentric loading still are the same as before, 37 megapascal, and the engineers assumed 0 bending stresses because of the high torsional stiffness of this box section upper flange. And this was more or less the starting point of our investigations. The question was, is this assumption correct to neglect the bending stresses at this position? So we started with finite element calculations. You see here the finite element model before retrofitting. So the girder without reinforcement plates, loaded again with 100 kilonewton, and in the diagrams we see the results. We see the vertical compression stresses over the length of the girder. So x0 means the position of the load introduction, and we have the results for 2 positions. On the left we have it for position 1, which is within the box section upper flange, and position 2 is 30 millimeters below the reinforcement plates. Notice the shown results are without reinforcement plates, these dashed lines. We see the distribution of the compression stresses from concentric loading in the mid plane of the web, and on the compression side we see larger stresses. So this part here between the red and the green, this is the additional torsional part. that is can be seen here. And in position 2 we have more or less the same behavior. We have smaller stresses and compression from concentric loading and also smaller torsional particles. If we now add these reinforcement plates, so after retrofitting we get the following results. Let's start with position 2. We see all new lines, all solid lines show the same results, so we have nearly no bending stresses in position 2. However, at position 1, within the box section upper flange, we still see significant local bending stresses. So the assumption of neglecting these bending stresses is not correct. So we moved on and did experimental tests on the real girder. We see the girder here, and we see in the right photo we see the load introduction, the eccentric load introduction on the rail with this device. We see here the reinforcement plates, and the left photo is taken from below, and we can see the strain gauges that have been applied. So these 3 strain gauges here are the measurement devices below the reinforcement plates, and these 3 ones are within the box section upper flange. Notice we had to cut a small hole into the reinforcement plates to be able to install the devices. These are the geometric properties of the girder. The tested part had a span of approximately 2.2 meters, and we had here transverse stiffness at the supports loading in the middle. The height of the girder is approximately 750 millimeters. The rail is a A55 rail, and it was measured in detail, as you can see here, and the abrasion was approximately 3 millimeters. These geometric properties, as well as the properties of the geometry of the weld and the web plate and the upper flange, were taken into account in the finite element models. Here we see the applied strain gauges. In total we had 12 strain gauges installed, 6 at position 1, these are the red ones within the box section upper flange, and 6 in blue at position 2 below the reinforcement plates, and 3 on each side. Here again you can see the small hole that was cut into the reinforcement plates. To the results for position 1, this is within the box section upper flange. We again have the solid lines are the numerical results, and we see here the measurement values. So this is the girder after retrofitting, so at the end of its lifetime, and we still see within the box section upper flange, we still see this significant bending stresses. So now it is confirmed not only numerically but also experimentally that we have here significant bending stresses within this box section upper flange. At the same time, on position 2, we find that there are hardly any bending stresses, so we have the same results more or less on both sides of the web. This is in line with the Eurocode predictions and with the numerical results. So we can pretty much ignore the bending stresses below the reinforcement plates. However, we need a proposal how to calculate these bending stresses within the box section upper flange, and therefore we developed such a model. Actually, it's quite simple. It consists of the upper flange, in our case it was a U section, and the reinforcement plates. Together they build this box section, and this box section should be modeled as a frame in a structural engineering software with beam elements, considering the actual thickness of each of these plates in the cross section. And the support is simply supported at the top junction and simply supported at the bottom junction, and the loading is the moment M, which is the wheel load Fz times the eccentricity. And the result of this calculation is the moment distribution M web, which we can see here, over the web height. Notice that the result M web is independent of the length the engineer chooses in longitudinal direction of the girder. So you can take 1 centimeter or 1 meter. We just want to know the moment here. So it's independent. However, we also want to calculate the stresses, sigma in the web plate. Therefore, we have to divide the moment, M web, by an appropriate section modulus. And this is defined by L effective T. This is our calibration function. This is the effective length in longitudinal direction times the thickness square divided by 6. And L effective T is proposed as L effective, which is the effective length of the concentric case. This formula already exists, this parameter, and can be calculated according to the Eurocode. L effective times a function of h over b, where h is the height of the box section and b is the width. If we now compare the results of an additional parametric study that was carried out with the proposal, we find the following. We plot over h over b, we plot the values L effective T over L effective, and the dashed line here is the design proposal. And data points above this dashed line are conservative ones. So we see here that the design model is able to accurately and conservatively describe the real behavior. As a remark, in the meantime, we also proposed a corresponding design formula for the case of a triangular reinforced upper flange. This is a more common approach nowadays for modern cradle runway girders. Notice the L effective formula is slightly different, but the main system keeps the same. For further information, please check out the following reference. Concluding, local stresses have been investigated by experimental tests and numerical calculations. And this is the main point. The local bending stresses in the web within the box section upper flange can be significant and should not be ignored for a fatigue design. However, the bending stresses below the reinforcement plates can fully be ignored. And finally, a new proposal for the calculation of the local vertical bending stresses was presented. Thank you for your attention.